All right. Good evening, everyone. Great to see another packed hall for one of our public lectures. So welcome all of you who have come, perhaps some of you for the first time. Many others, maybe you were there for the David Tong lecture a few weeks ago. ICTS, as you know, is a center for research in the theoretical sciences, in physics, mathematics, quantitative biology, and many other areas. We have a very active PhD program, and many of you who are in the sciences, you should definitely think of ICTS as one of your prospective areas. We also have many programs, activities, research workshops, especially geared towards master's and PhD students and other young researchers. And finally, a lot of outreach events like this one. And you may know about our Copy with Curiosity, which we hold at the planetarium. If not, you should check out it's our webpage and maybe subscribe to our mailing list or view our YouTube channel, ICTS Talks. We have over 55,000 subscribers, so you can get notifications of new material which we are constantly uploading on this webpage. So today, it's a pleasure to welcome all of you for one of our very special public lecture events in honor of Professor C.V. Vishveshwara, who also happens to be the founder of the Bangalore Planetarium, in addition to being a very eminent astrophysicist. And I will let Professor Ajit from ICTS tell you a few words about him. And so this is a lecture we instituted a few years ago. The inaugural lecture was given by Professor Kip Thorne, and that was a very special event, as you can imagine, and you can again watch the recordings on our YouTube channel. Afterwards, we've had lectures by Professor Lyman Page and Professor Priyambada Natarajan. And today it's a great pleasure to have Professor B.S. Sathyaprakash, who will deliver the fourth Vishveshwara lecture after a gap during the pandemic. We wanted it to be an in-person event, and while we had many online activities, this is a special event for us, and we wanted it to be in person. It's also a privilege to welcome Professor Saraswati Vishveshwara, wife of Professor C.V. Vishveshwara, but also a very well-known biologist at the Indian Institute of Science. And it's a pleasure to welcome her to this event as well. I will now hand it over to Professor Ajit, who will introduce the speaker, Professor Sathyaprakash, and also say some words about Professor Vishveshwara and this lecture series. So over to you, Ajit.
Thank you, Rajesh, and good afternoon, everyone. It's a great pleasure to welcome all of you again for this fourth C.V. Vishveshwara lecture. This was established in 2018 in honor of Professor C.V. Vishveshwara, an eminent theoretical physicist who has made pioneering contributions in the study of gravity and black holes. And many of you know his major contributions include proving the stability of the Schwarzschild black holes and understanding the universal features of perturbed black holes, which we now call as quasi-normal modes. And it's remarkable that in the last 7 years, we have been routinely detecting these signatures that was predicted by Vishveshwara and colleagues in the several decades ago, using gravitational observations by LIGO, Virgo, and other observatories. Apart from being an eminent scientist, Professor Vishveshwara was a man of multiple talents. He was a popular author and a very interesting speaker. If any of you have heard Professor Vishveshwara once, you would not forget him. He was also an accomplished cartoonist and has made very interesting cartoons on science and other aspects of life. We also heard from Rajesh that he also has contributed to building the science education and the scientific outreach effort in particular in Bangalore. He's a founder director of the planetarium in Bangalore, which continues to thrive. And we are very proud to have an association with the planetarium from the ICTS in the form of these monthly lecture series called Copy with Curiosity and many other aspects of science outreach. Today's VISHVESHWARA lecture, Professor B.S. Sathyaprakash is a world-leading expert in gravitational-wave astronomy. His pioneering contributions to the study of gravitational waves has been recognized worldwide. He's an elected fellow of the American Physical Society, the Institute of Physics in the UK, as well as the International Society for the General Relativity and Gravitation. And he's also a distinguished alumnus of the Indian Institute of Technology, Madras. Apart from his pioneering contributions to the gravitational wave physics and astronomy, he has played major leadership roles in the gravitational wave community internationally, both inside the LIGO scientific collaboration, which operates the LIGO detectors and produce these sort of very interesting results from the gravitational observations the last decade or so. And currently, he's one of the leading figures in formulating the plans for building the next generation of gravitational observatories, in particular in the US, which has the name of Cosmic Explorer. I'm particularly glad to have Satya as today's VISHVESHWARA lecturer. He grew up in Bangalore. In fact, his name is Bangalore Sathyaprakash. And as you also probably hear from Satya, probably, he has a very long association with Professor C.V. VISHVESHWARA. And we can't think of a better speaker to give this C.V. VISHVESHWARA lecture. So with these words, let me invite Satya to give this lecture. Before that,
before that, I would like to invite Professor Saraswati Vishweshwara to come on the stage and on behalf of ICTS, hand over memento to Professor Sathyaprakash.
Okay, thank you. Everyone can hear me at the back? Excellent. Yelrigu namaskara. Ellardu utaita. Okay, I'll probably speak most of the time in English, but I'm happy to answer questions in Kannada, which is my mother tongue, as you heard before. I'm truly honored to give this lecture. International Center for Theoretical Sciences is a world-leading organization. Today, whenever I go to conferences on gravitational waves and gravity and other aspects of theoretical physics, I meet a lot of students from Indian origin. And I ask them what motivated them to come to pursue this particular subject. And invariably, I get the answer that they attended a workshop in ICTS, they heard a lecture, or they had a school. And I think it's really a great institution where you can get inspired, you can learn, and you can become whatever you want, and nothing will stop you. And this great institution is promoting theoretical sciences in ways that were not available before. And I really welcome you to take this opportunity to learn from this institution. Today's lecture is about my mentor who shaped my career in ways that is difficult to say in a few words, but let me try. In 1978, when I was doing my final year degree, I was still pondering whether I will pursue music, Carnatic music in particular, or I will go to do physics. These were the only two options that I had in mind. And it was a rainy evening. It was the next year was going to be the centenary of Einstein's birth. And Narasimhaya, who many of you might know, was the principal of our college for many years. And he started a science series, over a month, there would be lectures every other day, maybe every second day or third day. And one of the lectures was given by Professor VISHVESHWARA, who had just then returned from completing his studies and postdoc in the US. And he talked about black holes. That was the topic, just 2 words, black holes. Very intriguing. In those days, nobody knew what black holes were. And far fewer believed in their existence. Today, we talk about black holes as though you can buy them next door, right? Everybody knows about black holes. But those days, they were not. But this was a pioneer who studied black holes, as I will describe later during my lecture. And he's talking to school students, and he described these fascinating objects in ways that really glued me to that topic. And it's very few people get to do what they decide on that day, on a particular day. And I was really lucky, because today I'm pursuing what Vishu told me about. He's Professor VISHVESHWARA, but we all call him with love Vishu. And I'm happy to be pursuing the topic he talked about. Some 15 years later, in a conference that was organized in Pune, it was his 60th birthday. He was honored with a book. And in the book, I wrote that one day I will come and tell you about a prediction that he had made during his PhD. I wrote it with a lot of hesitation and not sure that we will succeed. But it turned out that another 15 years later, we were able to confirm that very prediction. And I was very lucky to finally honor my mentor for my whole lifetime. So it's really a great pleasure to be giving this lecture today. So today's lecture is going to be about gravitational waves. Many of you may have heard about it, but I'm going to start with a prelude just so that those of you who are listening to this for the very first time might get some idea of what they are. This is what we discovered in 2015. So what you heard there is literally the oscillations of space-time. And this was discovered in 2015. What it is about is what I will tell you. But before that, these are gravitational waves first observed on 14th September 2015. So 15 is for the year, 09 is for the month, and 14 is for the day. You will see this number, this kind of number throughout. So let me introduce the convention. But before I tell you what gravitational waves are, this discovery was already awarded Nobel Prize in 2017. And the Nobel Committee says for decisive contributions to the LIGO detector and the observation of gravitational waves. They were awarded to Rainer Weiss, Barry Barish, and Kip Thorne, who were pioneers in many ways in making this discovery possible. But I want to put it out there right from the beginning that this discovery wouldn't have happened without the contributions from hundreds of PhD students and postdoctoral fellows. I'm going to honor them later on at the end of the talk. But believe me, this is not a discovery of a few people, but a large collaboration that made it possible. Big science today really comes from efforts of many people, and diversity is extremely important in making new discoveries. So what are gravitational waves? I'm going to show you a couple of equations. Don't be too afraid, because as Professor Tong 2 weeks ago told you, the most important equation of physics is this equation. What it tells you on the left-hand side is the geometry of space and time. And on the right-hand side is matter. Now, matter, just like, let's say, stars, black holes, When it moves, it alters the geometry on the left-hand side. Therefore, space-time, according to Einstein, is not static, it's very dynamical. And this dynamical aspect of gravity is what we call gravitational waves. And it is described this, what some people describe as the most beautiful equation in physics. Geometry on the left-hand side and matter on the right-hand side. Matter tells geometry how to curve, in the words of famous physicist John Archibald Wheeler, and in turn, the geometry tells matter how to move. Now, all that is fine, but what produces gravitational waves? It turns out anything that is accelerating, in principle, produces gravitational waves. We may not detect it, we may not observe it, but as I walk around, moving my hands, I'm producing gravitational waves. Luckily, most of the reason why I'm sweating is not because of the gravitational radiation, but due to electromagnetic interaction, it turns out. Gravity is very weak. Therefore, it's extremely hard to produce gravitational waves. And in order to move space-time, you need very compact objects. And these compact objects are signified here in the form of two neutron stars that are going around. If you have a single neutron star that curves the space-time around it, if you have two neutron stars going around each other, that creates a ripple that escapes from the source at the speed of light. And this is what we call gravitational waves. So what can produce the strongest gravitational waves? Today, I'm going to tell you a secret that not many people would know. And all you need is pre-university mathematics. So here we go. The coupling constant, the coupling that happens between matter and space-time is encoded in Einstein's equation. It is this. And it's made up of fundamental constants of nature, the speed of light to the power of 4 divided by Newton's constant. It does not have anything else in the coupling. How strongly matter can curve space-time is encoded in this. If you compute that quantity, c to the power of 4 upon g, it has units of force. You can verify that for yourself. And numerically, in human made-up units, it's about 10 to the 44 newtons. You might just ask, what is the meaning of that? 10 to the 44, 10 to the 80, 10 to the minus 2, what does it matter? Well, we can ask the question, under what circumstances can such a force be felt? We are not talking about any circumstance, but in a situation where gravity plays the role of dynamics. When gravity plays the role of dynamics, what kind of force will be felt by objects? The simplest thing that we can think of is a binary system. Two stars are going around each other, let's say. One star experiences this force, mv square upon r. Everybody is familiar with it. That's the centripetal force. It is supported by gravity. This is where gravity comes in. If any object moves with a speed v and its mass is m, this is the force felt. But if it is caused by gravity, it's really v square is gm by r. So we can eliminate m by r from this equation, and the force is v to the power of 4 by g. This is nothing but Kepler's law. And Kepler's law you may not have seen in this form. That's also Kepler's law. The force felt by an object moving with a velocity v is nothing but v to the 4 upon g. I can re-express that force by multiplying and dividing by c to the power of 4 in this form, where v by c is dimensionless because it's velocity divided by velocity to the power of 4. When Earth goes around Sun, its typical speed is about 1/millionth of the speed of light. Therefore, the force it feels compared to this fundamental force is some 24 orders of magnitude smaller. So it doesn't emit gravitational waves so strongly. And that equation immediately tells you, in order for us to have strongest gravitational waves, we must have V close to the speed of light. And it turns out, no matter how close you go to the sun, you will not accomplish that. Even Mercury, it's only V by C is some 10 to the minus 5 or 10 to the minus 4 at best, even if you go very close. So in order to accomplish this, it turns out we must approach C, and that's only possible if you orbit around a black hole or a neutron star. Those are the most compact objects, and therefore you can get very close to them. So what this tells you, the simple exercise tells you, is that in order to produce gravitational waves of sufficient strength, you must have black holes and neutron stars involved in the dynamics. Black holes and neutron stars in a binary system can really experience forces that are close to that fundamental force. Now, everyone knows what black holes are, but neutron stars are also very compact. If you take a 1 solar mass black hole, it's about 1.5 kilometers in radius to 3 kilometers. But if you take a neutron star of about 1.4 solar mass, typically that's their mass, they're about 10 to 15 kilometers in radius. We really don't know how precise the radius is. So these are not very different. They're as compact, almost as compact as black holes, and those are the ones that are going to produce very strong gravitational waves. In fact, black holes are so compact, when they merge, the luminosity in gravitational waves is far greater than all the stars in all the galaxies in the universe. So black holes, when they merge, no matter how massive they are, they will outshine the entire universe for a brief period of time. So although black holes are black, that is single black holes. If you bring two black holes together, their luminosity is far greater than the entire universe. So that's something that we can actually calculate even with a simple formulation like that, but I'm not going to do that. So the rest of this lecture, we're going to look at some pretty pictures and try to understand what is it that we have discovered. Still staying with the prelude, the part one is about discoveries that have already happened, and I'm going to talk about only two of them. The first one is GW 150914. That's we already came across. I introduced right in the beginning. This is what is called the waveform. Many of you might have written waves on a string, waves on a rope, guitar string, etc. It is similar. This is ripples in space-time itself. As a function of time, so this is time. This is about, overall, about 15 milliseconds all across. 150 milliseconds, I'm sorry, 0.3 to 0.45. And the waveform here has a few cycles. This is what was discovered. And the reason why we believe that these are black holes colliding is that you don't, the signal is there for a few milliseconds, and then after there is nothing. The thing that VISHVESHWARA discovered when he was a graduate student, and I told him, we are going to come and tell you one day, we have seen this in our detectors, is this final one cycle called ringing of a black hole. So when black holes are right out there, they don't do anything. But if you perturb them by kicking them, they're going to respond by emitting characteristic waves of space-time, which tells you what is the mass and spin angular momentum of that black hole. This is what Vishu was doing during his PhD, but not for spinning black holes, but for non-spinning black holes. That's what he had predicted. And when we made this discovery, it was completely consistent with his predictions. The masses of the black holes that were discovered earlier were so large, astronomers were not suspecting to detect such black holes. And this immediately generated the interest that probably these black holes did not even form by stellar evolution. Rather, they were produced in the early universe. The first two observing runs of LIGO and Virgo produced overall about 10 binary black holes in total. And that is what started off gravitational wave astronomy. But during the second observing run, in the final months of observations, we were extremely lucky to observe the collision of two neutron stars. And that event is called 1708-17, August 17, 2017. So what is this discovery? I consider this discovery so far to be the gem, the jewel, the crown jewel of discoveries. It consists of two neutron stars coming together. And when the two neutron stars come together, they produce very rapidly moving neutron stars, very energetic neutrons. And these neutrons collide with each other, produce very heavy elements. Those heavy elements decay, and they produce an afterglow, and that's called a kilonova that was observed within 8 hours. I have a story to tell, but I'll reserve it for another day. And this event was not only observed in gravitational waves, but just about 2 seconds after, we discovered gamma ray bursts coming from the same region of the sky. 2 seconds, and this event was about 120 light years. And a 2-second delay meant that gravitational waves are essentially traveling at the speed of light. And that meant that many of the theories that were invoked to explain something called dark energy had to be abandoned, because in those theories, gravitational waves had speeds different from the speed of light. It also identified, this discovery, sites where heavy elements like gold, many of you are wearing gold ornaments, they were produced in this collision. People thought before that in order to produce heavy elements, you need supernovae. Yes, it is true that probably supernovae are producing some heavy elements, but it turned out that neutron stars are prodigious sites of production of heavy elements. Not only that, this event gave us a new tools for cosmology, because it turns out that we can measure distances, which are very important in cosmology, distances very accurately using gravitational wave observations. And finally, this observation also allowed us to understand the structure of neutron stars, about which I'll come and talk to you a little bit later. So these were the first discoveries. Now moving on, the third observing run, which took place in 2019 and 2020. It had to stop abruptly when the pandemic broke out, but we discovered overall about 100 gravitational wave events. And what's shown in this diagram, the x-axis has no meaning. The y-axis shows 1 solar mass, 2 solar mass, 5, 10, 20, 50. These are all the black hole events, these in blue. In orange, we have binary neutron stars merging to produce either a black hole or a neutron star. Sometimes we don't know what it produced. And over here are the astronomical black holes, not gravitational wave detections, but astronomers discover it, and also radio and X-ray neutron stars. Now, overall, up until now, the LIGO-Virgo-Kagra collaboration has found 2 binary neutron star mergers. I've told you about only one. 2 neutron star black hole mergers, and tens of black hole binaries. Those are the discoveries so far. From these discoveries, we can learn many things. We have learned many things, but there are also new puzzles. The rate of merger of these systems is about 300 per year per gigaparsec cube. So that's what we conclude, but we don't observe that big a volume currently, we observe a fraction of that volume within which we have found only 2. Similarly, for neutron star black hole mergers, we have observed about 2, but we expect about 100 per year per gigaparsec cube. Once again, the volume that we observe is very small for neutron star black holes, and so we have observed about 2. In this case, they observed about 76. The merger rate that we conclude is about 25 per year per gigaparsec cube. You might ask, this is the smallest rate, and you have observed the largest number of them? What's going on? You must have made some silly arithmetic error. It turns out the heavier the system is, the greater the distance up to which we can observe. And consequently, the volume from which we are observing black holes currently is large. And that's the reason why it is 76. When we build better detectors, eventually, neutron stars are the ones that are going to dominate. And we will observe something like 1 million neutron star mergers every year. The volume from which we observe is so large, we will be overwhelmed by these two and not that. Okay. That's the overall statistical thing. But we have also observed some exceptional events. I already told you about one of them, 150914, and I'm going to spend 1 minute on each one of these new discoveries in the last observing room. The first one in my list is the second binary neutron star that was observed. The first binary neutron star, I listed a large number of different things. A kilonova was observed, gamma ray was observed. We even measured the Hubble constant, the expansion rate of the universe. But this particular one, this system is a pretty interesting one in that the simulation of this is not real data, but it is a simulation in which 2 neutron stars are going around each other. The final product, it turns out, is most likely not a long-lived neutron star, which produces all this kilonova, etc., but likely the 2 neutron stars came together, as you can see in this simulation. They merged together, they produced some little bit of ejecta, but that ejecta was not large enough, and the whole thing collapsed to a black hole. So there was no afterglow, there was no gamma ray emission. We observed nothing other than gravitational waves. So how do we know that this was a binary neutron star merger? Astronomers think that if the masses of the objects are between something like 1 to 3 solar masses, then they are neutron stars. If it is more than 3 solar masses, it's unlikely astrophysical processes will produce a black hole. Therefore, the masses that we measure are conclusively within the range 1 to 3 solar masses. So we classified this as a binary neutron star. In fact, more to the point, the neutron stars together have a total mass of about 3.4 to 3.7 times the mass of the sun. So if you divide that by 2, each one of them is about 1.8 maybe. That's all. This is the most massive binary neutron star ever observed. Nobody has observed such a system in our own galaxy electromagnetically. So this is a very interesting system from that perspective. But the reason why we probably did not observe electromagnetic radiation is because it was too far, 520 million light years instead of the 120 that I mentioned for 1708-17. So we don't know. The jury is out there. We need better detectors for electromagnetic telescopes. We need better way of localizing the source on the sky and so on and so forth. The second on my list is 1904-12. This is very special because in this particular case, for the very first time, we conclusively observed 2 black holes that are of very different masses. One of them was there somewhere here, 8 solar mass. The other one was 30 solar mass. They merged together, and in the process, they emitted gravitational waves not only at 2 times the orbital frequency, but also higher modes. And this is a big deal. In electromagnetism, electromagnetic radiation comes primarily as a dipole radiation. But there are also other radiation, like quadrupole, octopole, and so on. And in Einstein's theory too, the dominant radiation is what we call the quadrupole, but there are higher modes, and these higher modes are predicted by Einstein's theory and for the first time observed in this particular case. So the binary has unequal masses, 30 and 8. The heavier black hole has significant non-zero spin. All of this adds to producing this large mass asymmetry, and the spin produces this higher harmonics, which was observed in the system. The third in my list is an event called 1908-14. This is truly a gem of a discovery. It is for two different reasons. One of the primary has a mass of about 2.6 solar mass. I told you neutron stars could be 1 to 3 solar mass. We don't know exactly where, but all astrophysical observations with radio observations, X-ray, have shown us only neutron stars about 2.1 solar mass. It's a very big deal in nuclear physics and astrophysics. What exactly is the maximum mass of a neutron star? If it is really 2.6 solar mass, it's going to fundamentally change the nuclear physics as we know it, more precisely quantum chromodynamics. It's a big deal. In fact, it was Chandrasekhar, the Nobel laureate, Subramanian Chandrasekhar, who predicted almost 100 years ago, not quite, that white dwarfs have a maximum mass of about 1.4 solar mass. And in that case, the physics involved is far less complicated. It's Heisenberg uncertainty principle applied to electrons. So it's called electron degeneracy pressure. Neutron degeneracy pressure, which holds the neutron stars from collapsing, is far more complicated. It's quantum chromodynamics. And today we don't know what's the maximum mass of a neutron star. So we call this a mystery object. The heavier black hole, on the other hand, is 23 solar masses. We don't expect from astrophysical models an event like this to have happened so soon in our observing runs. After detecting maybe 1,000 events, we might have observed something like this. But we observed only about 70 or 80. We wrote a paper 1 year before with Professor Ajit here, saying that we need these kind of systems to test general relativity because they produce these higher modes. The previous one had higher modes. In this, you can see the higher modes literally in the data. I don't need complicated things. If you don't have these higher modes, this will be monochromatically increasing amplitude and frequency. In this case, we can see the modulation in the amplitude. We can see the modulation in the frequency. This is the gem of an event, but also a puzzle. Astronomers and astrophysicists don't know how to produce this binary. The final one in my list is 1905-21. This has generated more papers than the number of binary black holes we have detected so far. So we observed the event. It has probably about a cycle and a half, but look at the masses. One of them has 85 solar mass, the other one has 66 solar mass, and the two together merged and it produced 142 solar mass. You must be joking, right? If you add these two, it should be 151. What are you talking about? It's 142? Well, it turned out that something like 8 to 9 solar mass was converted to pure radiation in a matter of a fraction of a second. This is what I mean by saying gravitational waves outshine the entire universe in just a brief period. Moreover, not only such a great amount of radiation was created, but also this is the first observation of an intermediate mass black hole. It's the most distant binary at that time. We have more distant binaries now. And also the heaviest system at that time. I have a few words to say about it later on. The other interesting results that I won't say a lot more is that first one is about neutron stars, single neutron stars. Single neutron stars, if they spin and if they are perfectly spherically symmetric, they won't emit any gravitational waves. In order to push the space-time, that neutron star should be slightly asymmetric, like a mountain. How big a mountain? Well, a meter would do. A meter on a 10 kilometers will push the space-time and we will observe it. But it turns out that the fastest spinning neutron stars that we have in our galaxy, we know they exist, are so round that the mountain on them is less than a few millimeters on a 10-kilometer radius. I think these are the roundest objects possible. But what fascinates me is that we can sit here and build a detector that can tell you that the radius of a neutron star that is a few light years away or few tens of light years away, its radius is the same in all direction to within a few millimeters. I think that's fascinating. And that's what astronomy is able to do today. But the second one is even more interesting. It tells you that the energy in stochastic gravitational wave background. Gravitational waves could be produced in the early universe. That's like the cosmic microwave background that you may have heard about. And that noise of the formation of the birth of the universe, noise of the Big Bang, must have been very quiet because the noise seems to be less than a few parts per billion compared to the dark matter that is present around us. So that's fascinating. Now I'm going to switch and tell you about the new discoveries and puzzles in the next 10 to 15 minutes. The fourth observing run started last year. Advanced LIGO is now working very close to its design sensitivity. It was a sensitivity curve that was drawn more than 30 years ago, but LIGO has accomplished it, mission accomplished. The range to binary neutron star mergers increased compared to our very first observing run by almost a factor of 3, which means the volume from which we are observing is a factor of 30 larger. And black hole binaries are now observed several times a week. Let me show you that. This is the picture of alerts that were sent during the fourth observing run. The right-hand side, I will magnify it in a minute and show you. That was the first observing run. We observed 3 events during that first observing run. The second observing run, about 10, you can see here. And now we are shooting off O3A, O3B. O stands for observing run. And this is the fourth observing run. So we are accumulating events. This graph tells you that so far, until this morning, in fact, I put together this slide only this morning, we have observed about 78 significant candidates. They are listed. If you want, you can take a photo of this. This is where all public can follow. You can go to that website, and it will tell you what all events have been discovered. And it tells you the event ID, whether it's a binary black hole, binary neutron star. It tells you what is the possible source. It tells you when it was detected, what is called a GCN, a notice that was sent, and a possible sky location. Our sky localization is very poor, so normally you observe something like this. So this has been going on. The last event that we observed until this morning was on the last day of 2023. That was the event that we observed. It's a binary black hole, binary black hole, binary black hole, binary black hole. Well, you keep going, binary black hole, binary black hole. So far, all the events that I went only up to 27 November, the list goes on. So far, we have gotten tired with binary black holes. Okay? There are some new discoveries. You will hear about them later on, some puzzles and so on. But that's all we are observing so far in the fourth observing run. I can't tell you much more than that about the fourth observing run because the data is proprietary and it will be made public in about a year's time. Okay. I don't know what is happening. That must be the magic move taking its own time. Okay, part 2, puzzles. What are the puzzles? We have made all these discoveries. What did you learn by making all these discoveries? I think we probably jumped a bit too much. Yes. I told you about neutron stars, about 10 to 15 kilometers in size. We don't know whether the composition of a neutron star at its core is pure hadrons, meaning neutrons and a little bit of protons, or it consists of what are called free quarks. Neutrons are made up of quarks. But if you squeeze them too much, probably these quarks dissociate and become free. We don't know which one of this picture is true. And gravitational waves have the potential to tell you, but currently we don't know what it is. We don't know the maximum mass of neutron stars currently. That's a big puzzle. New gravitational wave observations are telling us there is possibly a 2.6 solar mass neutron star. That's a big issue because this diagram, which tells you the mass as a function of radius of the neutron star, which is called the equation of state, we don't know which one of these. There are many curves here. Some of them can contain pure quarks, others can contain strange matter, all sorts of things. We don't know which one of these curves, and they could be determined if we can measure both the mass and radius of the neutron stars. We don't know which one they are at the moment, because we can't tell whether the 2.6 solar mass object is a neutron star or a black hole. The prevalent theory until the discovery of 1708-17 was maybe the heavy elements are produced by supernovae, exploding stars. But all that changed dramatically. The theory was there, but it changed dramatically because we were able to observe this kilonova. That gave us the hint that many heavy elements in the periodic table are produced by merging neutron stars. This bright yellow, all those elements are produced in merging neutron stars. We do need supernova to produce some of the other elements. Of course, all the light elements are cooked in neutron stars. So we continue to be star matter, but things that are varying, the things, the gadgets that contain heavy elements, already they need neutron star binaries to have come together and collided. So, we cannot have the big technology and the jewels if life forms too high a redshift. That's the way I joke about this. You do need neutron star binaries to collide and form. We don't know how binary neutron stars form and evolve. I told you one puzzle about very heavy neutron stars. The origin of black holes. Are they formed by stellar mass black holes? Or are they formed by early universe? We don't know that. And one of the big puzzles for me is the effective spin, the rate at which black holes seem to be spinning in the binary, what is called the effective spin, which is a projection of the two spins along the orbital angular momentum. That seems to be close to zero. It's not a universal result because other authors find different results, but I just put it out there that this could be a puzzle. Moreover, we don't know how black hole binaries form and evolve, and the 1908-14 system that I mentioned to you is a big puzzle. We cannot explain how that forms. And I also mentioned to you this binary black hole merger. There was a chance coincidence of an electromagnetic observation after the merger of two black holes. Whether this is a common event that happens all the time, or is it only a chance coincidence? We don't know. And I mentioned to you about this 1905-21, in which one of the black holes was conclusively 85 solar masses. It turns out, no matter how big the progenitor star is, you cannot form black holes of masses larger than about 60 solar mass. And there is a good reason for it. So what happens is, when stars are cooking their elements by nuclear fusion, they produce this radiation. But when they exhaust all that radiation, all of a sudden the star begins to collapse, overheating the center, which produces radiation by further cooking of the elements. And that radiation is so intense that it produces particles, pairs. It's called the pair instability. It produces particle-antiparticle pairs, which suck out the energy. And consequently, the whole star comes collapsing because the radiation is taken out, the pressure is reduced, and the whole thing comes collapsing, but it hits the surface and explodes in a gigantic manner. And that leaves almost nothing behind if the stars are too massive. So that's a very big puzzle. We don't know what that produces. And finally, are LIGO-Virgo black holes, compact objects that we are discovering, are they really black holes of general relativity? Are they really showing us this quasi-normal mode that Professor VISHVESHWARA predicted many decades ago? We don't know the answer quite certain for reasons that I won't go into. But there are other problems with theory and observations. And I'll mention a few that gravitational wave observations might be able to resolve. There's what is called black hole information paradox. When black holes accrete matter, they're essentially eating away all that information. Although this is supposed to come out in the form of what is called Hawking radiation, for many decades, people believe that the information is lost. Today, many researchers, including those in this institution, don't think this is a problem, but there is not a universal agreement that that is the case. So I'm mentioning it out there that we might be able to solve the black hole information paradox. But whether or not the information paradox exists, black hole singularity is a big embarrassment for general relativity, because it is a single point in space-time where all matter comes together and everything becomes infinite density and so on, after which you cannot make any predictions, and that's the end of physics and blah, blah, blah. So this singularity is supposed to be cured by quantum gravity, but we don't have a viable theory of quantum gravity today. So this is a conceptual problem. And then there is the accelerated expansion of the universe. So what is this? This is related to something called dark energy. We know that the universe is expanding, but there is an accelerated expansion in the recent times. And that is produced, according to cosmologists, by something called dark energy. And the nature of it is not known. We also don't know what's the origin of dark matter. And these are all puzzles that exist today. One of the other puzzles that exists is what is called the Hubble tension, namely the rate at which the universe is expanding today as measured by two different experiments, the Planck and what is called the shoes measurement, which is here. They seem to be in tension. They use Cepheid variables. The other one is observing the cosmic microwave background right here. They seem to predict values that are very different from each other, so much so that it has come to be called the Hubble tension. And finally, in my list, we know that at the center of the Milky Way, there is a massive black hole. In order to produce black holes that are so big, how do we do that? I mean, can we assemble small black holes coming together and grow them? There is not enough time to do that in the universe. And these are the kind of puzzles that we might be able to observe with gravitational wave observations. So what are the prospects? What can we do? First, I want to tell you in a single slide, LIGO-India is going to be coming online. It will join the other observatories, strengthening what we can do. Laser Interferometer Space Antenna is a project by the European Space Agency. It will observe the universe at lower frequencies than what we are doing currently. But there are also plans to build larger detectors like LIGO, called Cosmic Explorer and Einstein Telescope. And I will say a few words about each of them. LIGO-India Observatory is now a project of utmost importance. It's a mega project. in India. It's going to be similar to LIGO, but when it comes online, our hope is that it will operate at the same sensitivity as LIGO detectors that are getting upgraded now. And this will add a massive baseline from the current observatories. And you know from fundamental physics, simple parallax measurements, longer the baseline, the better sky localization. Things like 1904-25, I'm sorry, which could not be localized very well, is now, it would be localized beautifully with LIGO-India. Einstein telescope is a triangular detector with 10 kilometers on a side, and it is going to operate as a xylophone detectors with 2 interferometers V-shaped, one like this, another 120 degrees, 120 degrees. So 3 interferometers, each hosting different detectors and different frequencies, will be really a dreamlike project because it will be able to observe the entire universe with black holes. Currently, there are 2 sites, one in Netherlands, the other one in Italy. The sites have been identified. Both the governments in Netherlands and Italy have committed funds to build these detectors. Unfortunately, neither government wants the detector to be built in the other one. So we are kind of stuck. If these 2 commit and say, hey, it doesn't matter, I'm for the science, it doesn't matter where it gets built, we have probably about 70% of the money. And then we can go and beg, for the remaining money. India, for instance, could give us some money and we could build a bigger detector. However, it's not clear whether that's going to happen. However, there is an effort to now build maybe 2 separate detectors. So maybe we'll go from a triangle to 2 Ls. That is to be decided over the next few years. The project that I'm currently working on is Cosmic Explorer. It's a detector simply 10 times bigger than LIGO. So what's Cosmic Explorer? It's a US concept for next generation observatory. It's a pair of detectors, one 40 kilometers, the other 20 kilometers, L-shaped surface observatories, roughly 10 times the sensitivity of LIGO today. Cosmic Explorer is envisioned as a NSF, that is National Science Foundation. So we don't have different agencies funding it. Hopefully, if they want to build it, that's it, we build it. And the Horizon study was completed in 2021. It's a technical design study that we had to do. If you have access to archive, then you can read all about what this detector can do. I will give you a summary. So this is my picture about what Cosmic Explorer and Einstein telescope will be able to do. In this plot, if you can reduce the light, because the entire series of plots is going to be very dark, I'm sorry. So if the team can reduce the light, completely turn it off, in fact. On the vertical axis, you see here the age since the Big Bang. That's when everything happened. 20 mega years is this. Those are what are called dark ages. We did not have any stars. The cosmic microwave background was freely streaming. And then we started to form stars which re-enhanced the universe about 500 mega years. This is about 5.9 gigayears, 12.5, 13.7 gigayears today. That's the vertical axis. But you can also measure it in terms of redshift. Some of you who may be familiar with the fact that universe is expanding, therefore, nearby objects have lower redshifts, farther objects have redshifts of 1, 2, 10, 20, etc. Now, on this plot, I'm going to show you the mass of the binary that we can observe and how far we can observe it. So this is the 40-meter Cosmic Explorer detector. In order to detect them conclusively, we need a signal-to-noise ratio of 8. And as a function of mass, this tells you how far we can see. So a 10 solar mass binary black hole can be seen up to a redshift of 100. What is the age of the universe at that time? Probably a few tens of mega years. Look at this. There are no stars. If we see something, that would be very interesting. But not only that, we can observe signals with very high signal to noise ratio, even at distances very far. These are the kind of distances that are not accessible even at signal to noise ratio of 8 for current detectors. But at those distances, we can observe them with super loud signal to noise ratio. Now, the signal to noise ratio 100 is not enough if you want to understand the structure of neutron stars, if you want to measure the expansion rate of the universe extremely precisely. And for that, we need signal to noise ratios of even greater. And even that will be accessible to us. So on this plot, I also show what would be the signal to noise ratio of 150914. That's our first event. It will not repeat, but there'll be other events similar. And they will be astoundingly loud in our Cosmic Explorer detector. That's 190521. That is such a puzzle today, but it will be completely resolved. And we will know what kind of system it was with Cosmic Explorer, super loud events. These are the kind of systems that we know exist in the universe. These are binary neutron star black holes. These are binary black holes, which we can observe there. And these are the neutron star black hole system. And these are the binary neutron stars in this system. And we can observe all of the neutron star black holes and binary black holes in the universe, and maybe almost all of the binary neutron stars. Okay. Now, if primordial black holes exist, they would probably be here, but we also have what are called population 3 black holes, which are black holes produced by fast stars. They will also be observed by Cosmic Explorer. But if these primordial black holes exist, most of them will be beyond our reach, but some of them will be observed by Cosmic Explorer. And in fact, this is not the complete facility limit. We will be able to improve the sensitivity such that we can capture some of those primordial black holes as well. So with that, let me just come to the concluding slide, which shows you how, as we improve detector sensitivity, we will be able to increase the reach of these detectors to greater and greater distances, redshifts, for binary black holes on the right-hand side, for binary neutron stars. This pink one is Cosmic Explorer, Einstein telescope, then LIGO-India, probably when it comes online, we'll be able to reach somewhere here or here. Those are the kind of limits that we will have. And this science wheel tells you the different science case, understanding the dynamics of neutron stars, black holes and neutron stars throughout the cosmos, and extreme gravity and fundamental physics. These form the primary science goal of our detectors. With that, let me not forget our PhD students and postdocs in many, many different universities. I'm sure you'll find ICTS somewhere there. Can you spot it? You can take your time. There are many Indian universities there, by the way, not just. There's also my alma mater, Indian Institute of Technology, Madras. There is IUCAA here, and all of them. So let me thank what you will become future. They are the ones who helped us make all this discovery. Thank you.
Thank you, Satya, for this very exciting summary of the status and prospects of gravitational-wave astronomy. I hope you'll be willing to take some questions. If you have a question, please raise your hand. One of our volunteers will bring a mic to you.
Thank you, sir. It was a wonderful talk. Will we be able to discover white dwarf binaries?
Not with the ground-based detectors, and I'll tell you the reason why. White dwarfs are about 10,000 kilometers in radius. And when they come together, their orbital frequency will be about a few hertz, maybe less than 1 hertz. And that's not accessible to ground-based detectors. We will be able to observe them with the laser interferometer space antenna. In fact, there will be so many observed that we can calibrate the LISA interferometer with white dwarf phylites. Yeah, so not with ground-based detectors, but with space-based LISA, we'll be able to do that.
Hello, sir.
Yeah.
It's a very exciting talk. I have from the fast equation which you have shown, on one side you have got the space-time curvature equation, and on the other side you have got the mass. Now, if when two black holes or they are merging each other, or the neutron stars are merging, now it creates the ripple and changes the space and time curve. If it changes the space and time curve, on the other side, it should change the masses. Are the masses of the stars and the other neutron stars are also changing when the merge is taking place?
Yeah, the system is continuously losing energy. The energy is produced by the mass. Therefore, the mass is reducing as well. And we take all of that into account when we compute the waveform, and that's used as match filter in our.
That means the masses of the stars which we consider are not remaining constant in that sense. Can it be said?
Individual stars, are they changing?
Yeah, it is happening. The individuals, the entire energy comes from the black hole, the individual black holes. So the total mass is what is lost to the system.
And how is the dark matter changing or affecting the gravitational waves? Which
The large mass,
dark matter. Dark matter.
dark matter. There could be, so dark matter will behave gravitationally in exactly the same way as ordinary matter. So if there are black holes that are made up of dark matter, we can't actually tell whether they are made up of dark matter or ordinary matter. But then the question comes from, oh, what about neutron stars? If dark matter is made up of neutron stars, I'll be able to just walk through it from the point of view of other interactions, but gravity will be severe. I will not be able to see it, even if it is next to me, but its gravity will be very, very strong. So dark matter, the gravity is. So it will also produce gravitational waves. In fact, one of the major research is to detect dark matter by using gravitational wave observations. That's, yeah.
Thank you very much, sir.
Yeah.
Excuse me. Sir, what future does eccentric gravitational waves have for astrophysics?
I'm sorry, can you repeat?
What future does eccentric gravitational waves have?
You mean eccentric binaries?
Yes.
Yeah. Binaries could be in eccentric orbits, but that eccentricity normally decays very rapidly compared to the way the orbits shrink.
Yeah.
Okay. Therefore, what LIGO is observing currently is they're not on eccentric orbits, but we are not looking very accurately for eccentric binaries either. However, even if there is eccentricity, that will produce gravitational waves, which will have special features present in the waveform. And I think the future is very bright for discovering eccentric binaries. Yeah.
Thank you, sir.
Thank you for the talk. Can we harness the energy of gravitational waves to, say, produce electricity or something else?
That's a question that is similar to what Heinrich Hertz was asked soon after his discovery of radio waves. I think a journalist asked him, hey, what can you do with these waves? Do you think you can harness? And somebody is supposed to have mentioned, can I tax it or something like that? You know, that's some joke there. My own personal feeling is this is not like electromagnetic waves, because the interaction is some 40 orders of magnitude smaller compared to electromagnetic waves. So I don't find how you can extract, even if you want to extract, you know, when it's a very important question for theoretical physicists, when gravitational waves pass by, the LIGO mirrors, are they extracting any energy from gravitational waves? My answer to that, if they are truly free masses, they probably don't absorb any energy. So constructing something would require a resonant mass detector, and the amount of energy absorbed when a gravitational wave passes is minuscule. And therefore, I don't see, you know, how you can build instruments that can extract. No, the resonant mass, there was a detector built, but I don't see a prospect of technological application of that. Yes, they do.
Sir?
Probably not. Yeah. Where is the question? Ah, okay. Yeah.
So I watched a video about black hole stars, and I think they could have formed supermassive black holes. But I have a question. They emitted a lot of gravitational waves, but they were quite early in the universe. So do you think they could be detected?
Yeah, they
Like
could be
gravitational
detected.
waves?
Yeah, as I showed you, when we build Cosmic Explorer, we will be able to observe mergers of black holes when the universe was only about 20 to 30 million years old. We don't expect stars to have produced black holes in that era. If we observe them, that must have come from the early universe, the primordial.
No, sir. So not black holes, black hole stars.
Black hole stars, what are they? Are they different? Yeah, they are the same.
No, sir, black hole
Or
stars.
supermassive black holes.
No, sir. So what I'm saying is when the universe was very small, so stars have a maximum growth limit because they expel radiation. But when the universe was small, the pressure would have stopped the radiation from being expelled, and the star could become very, very big. And that would allow a black hole to be inside. And that would be a pulsar.
Okay, I think they are called Thorne-Zitko objects. I think that's what you're talking about, or maybe something else. If you want to produce gravitational waves of considerable strength, you have to have compact objects.
Yes, sir.
Whether it is supernova or black hole, it doesn't matter. If it is not very compact, then it won't produce sufficient strength.
So there's a really massive black
mass doesn't
hole.
matter. The mass has to be inside a small space.
Yes, sir. So it's a really compact pulsar and it's spinning really fast. So do you think we would be able to detect that by gravitational waves?
No, or not unless there is some mountain on it. As I was trying to explain, if it is a perfectly spherically symmetric or what is called axially symmetric one, you won't see any gravitation.
But sir, then black holes are perfectly spherical, sir. So how do we detect gravitational waves?
Very good question. So if you have a single black hole, even if it is spinning very rapidly, you won't get any gravitational waves. Only if it is in the companion of another black hole, you will get gravitational waves. Otherwise, no. Or you can deform a black hole, as I said, by kicking it. I dare you to kick it, but anyway. A perturbed black hole could emit gravitational waves. Not a perfect, single black hole. If it is sitting there, it won't produce any gravitation.
Yes, sir. So a binary black hole won't be perfectly symmetric.
Correct. That's the reason why, it's not perfectly symmetric. It's like a dumbbell, right? If you put one black hole here and another black hole there, it's not spherically symmetric. That's why it produces.
Okay, sir.
Okay.
Thank you, sir.
Thank you for your wonderful question.
Good evening, sir. Sir, what happens, what can theoretically happen if an object crosses the event horizon of a black hole? What happens to gravity and space-time?
If you simply cross the event horizon, nothing much happens. No, it won't. In fact, if you have a big black hole, a supermassive black hole, if I pass the event horizon, I wouldn't even know. Only if you make the black hole smaller and smaller in mass, something called the tidal disruption happens. And the smaller the black hole, greater is its curvature. And that's the reason why we can constrain, for instance, general relativity with binary neutron stars and stellar mass binary black holes than with supermassive black holes. So if you simply cross the horizon, nothing much happens.
So there was a theory that if an object crosses the event horizon, and if we are observing it from Earth, then we'll see that the object is stuck in space. Correct. Like it's not moving.
That is correct.
Like what causes that?
This is because time slows down as you approach the event horizon. And the signals that are emitted by the object as it falls take longer and longer to get to you. Even though the astronaut in the let's say spacecraft that is falling is sending equal, radiation at equal intervals according to his clock. For us, they take longer and longer at later times. And this is what is called the gravitational redshift. It has been very accurately confirmed in the laboratory. More to the point, the reason why your GPS clocks work correctly is because this redshift effect has to be corrected. Otherwise, your GPS clocks don't work. So we know gravitational redshift is a true effect, and that's the reason why it appears as though the object is hovering near the horizon. But as far as the astronaut is concerned, nothing special happens. The astronaut simply passes through the horizon. No big deal.
Thank you, sir.
Sure.
Namaste, sir.
Namaste.
Sir, it might be a silly question, but I was just curious to know that we have seen binary black holes merging and binary neutron stars merging. Why didn't we see 3 black holes merging or 3 neutron stars like that?
Wonderful question. This is not a silly question. Let's clap for this question. There is a almost a rule in astrophysics or astronomy that you can't put together 3 objects and get them to orbit around each other, at least not closely. So astronomical objects somehow like to be in pairs and not threesome. And the reason for this is mainly due to gravitational interaction itself. You might ask, hey, what are you saying? You can see our solar system contains so many of them. Why don't we see the same thing? Yeah, that's because sun is the most dominant one. And after that, it is Jupiter. All others are almost negligible masses. So that can happen. However, over millions of years, what happens is if you have 2 black holes going around each other, anything smaller, they tend to scatter them off. They don't want to live in a multi-body system. They want to be just in pairs. And I can tell you in more details from using simple Newtonian physics and scattering. If you have 2 objects and a third body comes in the scattering experiment, the lightest object goes away because that gets the highest velocity. You can do this calculation by just using simple Newtonian mechanics. So that's the reason why we don't. But there are people who are predicting that some of the things that we are seeing, especially 1905-21 that mentioned very heavy masses, they think that there were 3 black holes, 2 of them merged and produced this 85 solar mass. And then the third one, which was far away, has now come together and merged. So not a silly question. In fact, there is no such thing as silly question. If we don't ask the question, we remain silly. So thank you for your question.
Good evening, sir.
Good evening.
Sir, my question was, how does the primordial black holes, does the primordial black holes can form the stars? Does it help to formation?
Yeah, in the very early universe, you cannot bring the matter together because they are heavily energetic, extremely energetic. We are talking about processes in the first fraction, tiny fraction of a second, when the universe has large fluctuations in density. Okay, some regions are overdense, some regions are underdense. On average, they're not able to collapse. But occasionally, because of some chance, you produce a very overdense region, and that can collapse to form a black hole. And this can predominantly happen during what is called the QCD phase transition, quantum chromodynamic phase transition, when the pressure all of a sudden goes down, and then matter is able to collapse, but only momentarily. And that's when the primordial black holes can form. However, you can't form stars because gas is very energetic. It's gas meaning it's only hydrogen at that time, mostly hydrogen. So you can't really form stars in the early universe. Matter has to cool down. And today, astronomers think, astrophysicists think that you can form stars only after something like 50 mega years, not before that.
Sir, but primordial black hole means black holes will form only at the end of the star's life.
No. Oh, that's correct. By stellar processes, black holes form after stars form. The stars have exhausted all their nuclear fuel. We are not talking about forming black holes via stars in the early universe. They directly collapse to black holes. No stars, nothing. They directly collapse. The gas collapse because of what is called an overdense region, which cannot hold itself. In spite of all the energy, it collapses. No stars. It avoids all the intermediate steps in forming black holes.
Thank you. Hello, sir.
Yeah.
Sir, what are your thoughts on multiverse hypothesis?
I don't.
Multi-universe hypothesis.
Yeah. No, I heard you. I was going to say it's a matter of faith, and I'm not a person of faith. So you can conclude whatever you want from that. The reason why I say this is currently we don't know how to test. By the way, this has nothing to do with what I talked about. I don't know whether I should be answering or not. However, the point is multi-universe by definition, you can't observe the other universes. And my question has always been, yeah, these are beautiful theories that produce multi-universes, but how do we test them? Let me leave it with that.
So, Satya, there is a related question from YouTube on the stability of triple systems.
Yeah.
There is this Leo triplet, 3 galaxies in a system, and then they orbit at their common center of mass. So how are they stable? How do they exist? How are they stable and how do they exist?
Okay, the central one has to be very tight and the third one is very far away. In that case, you can, and the mass difference has to be large as well. For the 2 close ones are heavier and the third one is a lighter. In that case, the one that is the pair that is orbiting close by acts as a overall mass for the third one to occur. So in this case, you can form, but you cannot form closed triple systems. You can form triple systems in which 2 of them are very tight and the third one is very far away.
Sir, yeah, here, sir.
Where is it?
Center, sir.
Okay, please go ahead.
Yeah, you mentioned in your the set of open problems that gravitational wave observation can help quantum gravity and to tackle the problem. So what kind of observation do we kind of look for? How do you even go about trying to conceptualize the problem of trying to tackle quantum gravity?
Yeah, I personally don't think gravitational wave observations will resolve the problem of quantum gravity. However, this is a field which is very active. There are papers that are coming out that are talking about modifying the structure of the black hole horizon due to quantum gravity effects, even on macroscopic black holes, like stellar mass black holes. We have to take that seriously. Any opportunities to test quantum gravity comes completely free. So we can do it. But I'm not convinced that quantum gravitational effects will appear on macroscopic scale, but I might be even in the minority, by the way. There are lots of people who are very enthusiastic about discovering quantum gravitational effects, either via propagation, but I don't think gravitational waves will do because the wavelength is too large, or in black holes. But that's our best bet anyway. There's probably no other way to detect quantum gravitational effects.
Thank you, sir.
Sir, okay, so after electron regeneracy pressure fails, we see the formation of neutron stars. But after neutron degeneracy pressure fails, we are directly seeing black holes. Shouldn't we expect an intermediate compact object made of quarks?
Absolutely. Absolutely. That is the thing that we don't know. So today, one of the big puzzles is whether or not matter goes through a phase transition. When you keep increasing the mass of the neutron star, the core might squeeze out the quarks and form quark-gluon plasma. Is that phase stable to have a long-lived quark star, or is it going to collapse almost without any delay? Is a big question, and that question we can answer with Cosmic Explorer. We will be able to tell because we can measure the mass of the object, we can measure the radius of the object, and therefore we can conclusively also observe what are called twin stars. One star has undergone phase transition, so it is small. The other is big because it is not yet undergone phase transition. Almost the same masses, or even the same masses. And when we observe something like 1 million neutron stars with Cosmic Explorer every year, I bet we will begin to observe these twin stars. Yeah, absolutely. Wonderful question.
On a related note, you mentioned that there was an object observed of 2.6 solar masses. What is the possibility that it could be something like a quark star?
We don't know because we can't measure its what is called tidal deformability. At the moment, we can't. The limits that we can set on its tidal deformability is not good enough. But if we observe something, close by with Cosmic Explorer, or even 1908-14 with Cosmic Explorer, we will be able to tell whether it's a quark star. Currently, we can't. We can't tell.
Got it, sir.
Yeah. Thank you.
So, over here. Over here.
Is one person here? No. Yeah.
So you talked about the information being lost beyond the horizon of a black hole. So I was wondering whether the information is really lost, because when you consider hypothetical situation where you have two entangled particles and you send one particle inside a black hole, in order to spin should be conserved, right? So if you measure the one object, can you tell it is preordained the other object spin? So whether the information is lost, because you can without having to measure the other particle state, you can just measure the particle which is outside the black hole and determine the state of the other particle.
Yeah, it's not just by particle creation, sending one particle inside and another particle out to the infinity. You can change the mass of the black hole. You can just accrete all of the mass, no pre-creation. In which case, you can put a piece of paper with information written. Sathyaprakash gave a visual lecture and put that paper inside. The question is that information lost? Quantum mechanics tells no information can be destroyed. But this is a paradox that most people today don't think it will be lost. Eventually, when the black hole evaporates, that information is still preserved in the radiation that comes out. In the past, it was thought that that information was lost, but there is not complete consensus, but I believe the majority of theoretical physicists think that the information is not lost.
This radiation is not the Hawking radiation,
Not
right?
lost.
This radiation you're talking about, it's not the Hawking radiation, right?
Yeah, the final radiation is the Hawking radiation. The final radiation that comes out, but for the kind of black holes that we are talking about, they won't radiate even in one Hubble time. They will take thousands of Hubble time. But this is a question of academic importance. I don't know whether we can construct black holes that can be observed, with Hawking radiation. There was some attempts in the CERN collider experiment to do this. But there are also what are called analog black hole experiments. Whether they will become mature enough to test these principles is certainly something that is currently being considered, debated. So they're what are called analog black holes. So maybe it's possible to test the black hole information paradox with those experiments. I've heard several talks on that.
All right, sir. How are the single neutron star? You talked about single neutron star producing gravitational waves. If they have this mountain on them, how are these waves different from the gravitational wave produced by two binary black holes or neutron stars?
Did you hear that?
How is the gravitational waves from a spinning neutron star different from that from a binary?
The amount of energy that is lost by a spinning neutron star is very little compared to that of a binary black hole or a binary neutron star. So the energy leaks out very slowly. So these are systems that will last for millions of years in our band. So we can observe them anytime we want, but they will be simply continuous waves. It will be like a single sound. A very bad musician like me, it will be the same thing, no harmonics, nothing. It will sound like that. Whereas a chirping signal, orbiting signal, whoop, that will be the sound. So they are different kind of signals from these systems.
Thanks.
Yes, sir. In a last talk that I attended somewhere, it was said that in low mass X-ray binaries, the mass transport occurs through that Roche loop, through the Lagrange points. Can that mass transport cause gravitational waves?
No, it will. It will cause gravitational waves. However, we won't be able to observe it. It will be too weak.
How small should the Lagrange point be in order to detect it somehow?
They really, in order to observe them in our LIGO detectors, it is not enough for matter to accrete incoherently. There has to be coherent motion. Otherwise, each blob that is orbiting and accreting will produce gravitational wave, but they will all be incoherent and they will produce some noise. Then they can't be observed. And first of all, they'll be weak, but they will also be incoherent superposition, and therefore we won't be able to observe them.
Hello, sir. Here.
Yes.
So I wanted to know if the expansion of our universe will affect our observations in the future.
Absolutely.
How so, sir?
That's a great question, which I never answered. My God, you guys are really smart. It turns out that if we observe a black hole of mass, 10 solar mass, from the universe when it was expanding 2 times faster, the mass will appear to us to be 3 times larger. So if you know what is redshift z, it will be 1 plus z times the intrinsic mass of the system. So it will appear to be larger mass. So absolutely, that's what in fact it will eventually limit. If you keep putting these objects farther and farther, they will appear to be larger and larger, and therefore lower and lower frequencies, and they will simply move out of the band.
So we will just have to find newer
We
ways
won't be
to
able to
observe
observe
it.
it. Yeah, absolutely. Wonderful question.
Thank you, sir.
Yeah. The simplest questions, by the way, are the best questions, as you can see.
There are many questions, but we have to wind up fairly soon. So we'll take last 2 questions and then stop.
Yes.
Excuse me, sir.
Yes.
Can, theoretically speaking, can black holes and wormholes exist in a subatomic level? And do you think we can solve EPR paradox using 2 particles interacting via wormhole?
Not my cup of tea.
Maybe you should just stick to this particular topic of the lecture.
Yeah.
And move on.
Not my cup of tea. I don't know much about quantum mechanics.
And another one, can you map the inside of a black hole using Hawking radiation? Let's say those 2 particles which went inside.
In a way, yeah. In a way, yes. In the sense that Hawking radiation will tell you what the black hole was made up of. In that sense, you can explore. Not in the way that, oh, it's a stable black hole. It won't emit, if it's a stellar mass black hole, it will not. But if it's a very tiny black hole, then it would emit Hawking radiation. It will tell you what it was made up of, what went in. Hopefully, if the information paradox is completely resolved, then I think, yeah, that's what it is.
We will take the last question.
Hi, sir. My question is, what exactly is the source of gravitational background? When you talk about cosmic microwave background, you can see up to 380,000 years ago. That's when light was free to travel through the universe, right?
Yes.
So when you talk about a gravitational wave background, my assumption is that you're talking about the Big Bang itself. So can we see up to 0th second? If so, what exactly do we expect to learn from that?
Wonderful question. In fact, it's the holy grail of gravitational wave cosmology. One day, we hope to be able to detect what are called primordial gravitational waves. And these gravitational waves are produced by quantum fluctuations that produced everything that is around us, including the radiation, Earth, human beings, Everything was produced because of matter that was created in the early universe. Matter was created in the form of hydrogen, admittedly, in the not even hydrogen, protons, maybe not even protons, quarks, to go back. So some matter was created in the early universe. Radiation was created. Why not gravitational radiation? It could be created. And there are currently only theories that say gravitational waves must be created. And there are other theories that say gravitational waves should not be created. Now, what do we learn? There are two things. One, we confirm which theory. But most importantly, we probably will try and understand the quantum gravitational effect. Somebody asked, is there any hope of understanding quantum gravity from gravitational wave observations? I think the answer is gravitational waves from the early universe. But gravitational wave background could also be created by a superposition of astrophysical gravitational waves, right? There are many, many binary neutron stars that are coalescing. I mentioned some million neutron stars every year. There'll be 100,000 binary black holes. There'll be 200,000 binary neutron stars. The addition of all of them could produce a background as well. That is just what we call astrophysical background. But what we are interested in detecting is the primordial black holes, and that can certainly tell us, or rather, we can hope it will tell us about the birth of the universe and the quantum gravity.
I think this is a profound enough point to be pondered over a cup of coffee.
Yeah.
So
before you finish, are there any National College guys here? Okay, a few. Hello, I was in National College many, many years ago. Okay, with that.
So let's thank Satya for this wonderful lecture and patiently answering all the questions.
Thank you.
And please join us for a cup of coffee outside before you leave.